Lagrangian optimization is one of the key tools in intermediate microeconomics. Within the standard economic model, we're often trying to find a maxima or a minima, but with a twist. We're trying to find the maxima or minima subject to some kind of constraints. Here, we're going to look at the theory behind how we do Lagrangian optimization. It's usually not enough to ask, how do I minimize the aluminum needed to make this can? The answer to that is clearly make a very, very small can. Instead, you need to ask, how do I minimize the aluminum while making sure that the can will still hold 10 ounces of soup? Or similarly, how do I maximize my factory's profit given that I only have $15,000 to invest? Lagrangian multipliers can be useful when faced with such a task. A typical problem for a consumer would be to maximize utility when deciding to purchase between, say, two goods, think indifference curves, subject to some constraint, think budget constraint, when we have these different prices of these two goods. And that is, in essence, constrained optimization, right? You created budget constraints with indifference curves, and now we look at them as equations in this Lagrangian optimization approach. There's two things we need to consider when we optimize with constraints using the Lagrangian approach. The two things that we need to consider are, just like in indifference curve analysis, our budget constraint, the slope of the budget constraint, and our indifference curves, or the slope of the indifference curves, which gives us the marginal rate of substitution. So first up, let's look at our budget constraint. Here we have an assumption that we use all of our income on these two goods. And what we have is M is equal to our income, or our budget, is equal to the price of X times the quantity of good X that we consume, plus the price of Y times the quantity of good Y that we consume. So we're assuming within this framework that the consumer spends all of her income, and this would be the basic setup of our budget constraint, very similar to what we can do with indifference curve analysis. From basic economic theory, we also know that our optimal bundle will fit with what's called the equi-marginal principle, which is the marginal utility of X over the price of X is equal to the marginal utility of Y over the price of Y. Some people call this our overall consumer equilibrium. Now, why is this true? In equilibrium, the marginal rate of substitution, or the slope of the indifference curves, this is showcasing the relative benefit of the goods. And this relative benefit of the goods has to equal the relative price ratio of the goods. So the slope of the budget constraint is showcasing the relative cost of the goods, and the slope of the indifference curve is showcasing the relative benefits of the goods. And so what we have to see is that the slopes have to be equal here if we're optimizing. All right, so how do we get from our indifference curve analysis to the equi-marginal principle? The equi-marginal principle is showing that the marginal utility of X over the marginal utility of Y is equal to the price of X over the price of Y. And when we do indifference curve analysis, all we're saying is that the price ratio is equal to the marginal rate of substitution, the slope of the indifference curve. How do we translate that over to the marginal utility of X over the marginal utility of Y is equal to the price ratio, right? So how do we end up doing that? Well, we can see here that at this point, we have a marginal rate of substitution of 3. So if we look at this graph and we're at this point right here, we have this marginal rate of substitution equal to 3. For every additional 1 unit of X that we get, we would have to offset that with 3 units of Y to remain equally happy with this outcome, or indifferent between those two scenarios, right? So the marginal rate of substitution here is 3. We know that at that point, the marginal rate of substitution is 3. Okay, that's from indifference curve analysis. What does that do for us for translating us to the equi-marginal principle? Well, at that same point, we could then logic through and say 3 Y's give us the same utility as 1X, right? It's leaving us indifferent. So the marginal utility of X is at a 3-to-1 ratio when compared to the marginal utility of Y, 3 y's are giving us the same amount of utility as 1x. So the marginal utility of x is equal to the utility from 3 y's that we get at this point. So what we can say is that the marginal rate of substitution is equal to the marginal utility of x over the marginal utility of y. In the last case, our marginal rate of substitution of xy was 3. And then at that point, what was our marginal utility of x? Well, our marginal utility of 1 unit of x had to be 3, whereas the marginal utility of y is only 1, right? It took 3 units of y to equal the same utility that we derived from x. So our marginal utility of 1 unit of x gives us 3 utils, and our utility from 1 unit of y would have to be a third of that. And so we are at this 3-to-1 ratio here. So it turns out that our marginal rate of substitution is equal to our marginal utility of x over our marginal utility of y. So from indifference curve analysis, we already know that the marginal rate of substitution has to be equal to the price ratio. Basically, the indifference curve slope has to be the same as the budget constraint slope. Now what we've done is we've shown that that slope of the indifference curve also has to be equal to the marginal utility of x over the marginal utility of y. And so from this, we know that we can just get rid of the marginal rate of substitution here, and we still have a truth that the price of x divided by the price of y is equal to the marginal utility of x divided by the marginal utility of y. With this new relation that we have an equation that we can now rearrange, and it's going to turn into something that looks awfully familiar. So if we multiply each side by the marginal utility of y and then divide each side by the price of x, what we end up with is the equimarginal principle. We end up with the marginal utility of x divided by the price of x is equal to the marginal utility of y divided by the price of y. So what is the equimarginal principle really saying to us? If we have the equimarginal principle, if we have the marginal utility of x over the price of x is equal to the marginal utility of y over the price of y, then what we have is our marginal rates of substitution, or the slope of the indifference curve, equal to the price ratio, or the slope of the budget constraint. In other words, if we're at the equimarginal principle, we are at an optimal point on our analysis. The equimarginal principle also gives us what some call the marginal utility income, or the shadow price. It's basically saying if we got a little bit more income, how much more utility would we get from these various goods, right? So we can, if we relax our budget constraint just a little bit, how much more utility can we get? That's what we get from this relationship here, the marginal utility of x over the price of x, right? The marginal utility from getting a little more income, or you could do it with a little bit lower prices, right? When you relax the constraint, how much more utility do you actually get? So what would be the prices that optimizers would pay to kind of loosen the constraints, or how much benefit do they get when the constraints are actually loosened? More formally, the shadow price is the value of what we call the Lagrange multiplier. And it's the value of the Lagrange multiplier at the optimal solution, which means that it is the infinitesimal change in the objective function arising from an infinitesimal change in the constraint, right? So when we change the constraint just a little bit, how much more utility do we get? That is our Lagrangian multiplier that we have here. And our Lagrangian multiplier, lambda, is going to be equal to that equimarginal principle. So when we're optimizing, we're trying to balance everything out so that the Lagrangian multiplier is equal to the equimarginal principle. It's equal to the marginal utility of x over the price of x, and it's also equal to the marginal utility of y over the price of y, because the equimarginal principle is saying the marginal utility of x over the price of x is equal to the marginal utility of y over the price of y. And so if we know this has to all be in balance, we can kind of transform some of this and build it into what's going to be important for our Lagrangian approach to constrained optimization. So let's manipulate these equations a little bit further, and we can see how all of these equations interconnect. So if we have lambda has to be equal to the marginal utility of x over the price of x, we could rearrange this sum and end up at a situation where the marginal utility of x minus lambda times the price of x is equal to 0. This is saying the same thing as lambda is equal to the marginal utility of x over the price of x, right? We've just rearranged the equation. The marginal utility of x minus lambda times the price of x is equal to 0. This is also saying the same thing as the marginal utility of income is at the optimal level. This form of the equation, however, the marginal utility of x minus lambda times the price of x equals 0, is going to be really important to understand when it comes to doing the Lagrangian approach to constrained optimization. This is going to be one of the equations that we're actually looking for. So we're going to utilize this concept, the marginal utility of x minus lambda, the Lagrangian multiplier, times the price of x equal to 0. We're going to use that knowledge that means that the marginal utility of income is being spread around at its optimal level with this equation right here. So this is one of the equations that's going to be a building block for what we're going to do going forward with constrained optimization. So look out for that kind of format there, the marginal utility of x minus lambda times the price of x equaling 0. And then obviously we can do the exact same thing, but then just change the x's to y's. So we're also going to need to utilize this equation with our Lagrangian approach to constrained optimization. The marginal utility of y minus lambda times the price of y will be equal to 0. That's the same thing as saying that our marginal utility of income is being utilized at this optimal level, that our Lagrangian multiplier is equal to the equimarginal principle, and so on. So we set things up saying that there's really two things that we need to consider when we optimize with constraints. And the first is really that equimarginal principle. The marginal utility of x over the price of x is equal to the marginal utility of y over the price of y. And we've shown with the Lagrangian multiplier what those have to be equal to. Now we're turning to the other part, the budget constraint. And this is a lot easier. All we're saying is the budget constraint has to get used. So when we're doing the Lagrangian approach, what we're really looking for is this format of the equation right here. We're going to just rearrange the idea that our income or our budget is equal to the price of x times the quantity of x plus the price of y times the quantity of y. Then we just rearrange that with some basic algebra to get the point where we end up with the negative price of x times the quantity of x minus the price of y times y plus our income has to be equal to 0. So minus px times x minus py times y plus m equals 0. So be on the lookout for this format. So we've shown three equations that we're going to be on the lookout for, and these three are going to be incorporated into our Lagrangian approach to constrained optimization. So with Lagrangian optimization, here are kind of the three equations that we're on the lookout for. We said really we only need to consider two things. We need to consider the equimarginal principle, the idea that we're in consumer equilibrium. When we're optimizing with constraints, we got to have the consumer such that we kind of have this balance between how much we're purchasing x and y, the marginal utilities of x and y. They're going to be equal to this Lagrangian multiplier. So we have these two equations that we're on the lookout for right here. And then the second thing that we have to be on the lookout for is our budget constraint. And so we have that here. We're just saying with this format of the equation that we're utilizing that budget constraint. And so just like within difference curve analysis, what we have to do is we have to line up our consumer preferences with our constraints when we're doing constrained optimization. And so we can almost think of this element as representing the indifference curves, and this equation down here is representing our budget constraints. And what we have to do is we have to get all of these aligned so that we can showcase mathematically that we are optimizing within this situation. And so that's what we're going to do with our kind of step-by-step process to solving Lagrangian optimization when we have constraints. And so that's what's up next. If you want to know how to do Lagrangian optimization with constraints, click on the thumbnail here to move to the next video.